Welcome back. So we have been looking at some problems and how to use various tools and techniques to solve the problems, and also we started looking at graph theory. So we continue with our study of problems using graph theory. So in this video we will be focusing on the handshake problem, which basically says that if in a room you have two N people, some of them shake hands with each other, but the guarantee is that if A shakes hands with B and B shakes hands with C, then A does not shake hands with C. If this is the condition, then what is the maximum number of handshakes possible? Now in the last video we saw that this particular problem can be modeled using graph theory. So let me quickly go over the introduction of graph theory once again. So we would like to model this problem using the language of graph theory. So a graph consists of vertices or a certain set of elements v1 to vn and a set of edges which are basically pairs of vertices. So edges is e1 to em, where k is a pair of the form vij. So some particular pairs of the vertices contribute to the edges. So the graph is given as v, as the two sets, the vertex set and the edge set. We usually denote it as g equals to v, e. Now there are some basic definitions. So if g is a graph and if there is an edge between u and v, and then it implies that there is an edge between v and u, that means the relation uv is a reflexive relation. In that case, we call that graph an undirected graph. Right? Sometimes for modeling purposes we will be assigning some weights to the edges, and in that case we call them as a weighted graph. If there is an edge from u to v, we say that v is a neighbor of u. Right? And in an undirected graph, the number of neighbors that are there of v is called the degree of v. So this is the number of edges that goes out of v or goes into v. Since it is undirected, they are same. So these are the basic definitions that we have. So visually, we usually denote the graphs using these blobs and lines joining the blobs. So these blobs are what we call as vertices. So in this place we have vertex A, B, C, D, E, F and G. And the edges we denote with a line. In the sense that if I have an edge like this, it means that A, D, because there is a line here, A, D is a pair. Similarly, A, B is a pair in the edge set, and so on. Now, since there is no edge between A and C, so A, C is not in the edge set. Is not in the edge set. Right? So usually we visualize this whole graph as something like this. Now we can have edges, we can put some weights that can be used for modeling of a problem. In that case we denote it like this, or we draw it like this rather. And as we told, the edges can not be undirected, in the sense that I can have direction, meaning D, A is there in the edge set doesn't imply A, D is there. So how do we denote that at the pictorially? So we denote it by the arrows. So the arrow implies that there is an edge from D to A, or in other words, D, A is an edge. Similarly, there is an arrow like this which is between D, A and B. we have this arrow in both directions. So this basically means that both A comma B and B comma A are in the X set. So when we have something of this form, we call it a directed graph. Of course, since in this example we have weights on it, so we call it a weighted directed graph. Okay. So the advantage of graphs is that they are very nice or very useful data structures to represent binary relations. They are very simple and yet very general. They can be used in an enormous number of ways for modeling an enormous number of problems. So let's see how this graph can be used to visualize a particular problem. So you recall this problem that we are looking at, the handshake problem. So how do we convert it to a problem or a problem on graphs? So first of all, we have to define the graph. So to define the graph, we start with defining the vertices. So we have 2n people. So for each people we denote a vertex. So the vertices are v1 to v2n. Now the relationship that we have to put, or in other words, the edges that we have to put should come from the problem. So in this case, we say that we draw an edge between Vi and Vj if the person Vi and Vj shook hand. Note that since Vi shakes hand with Vj also implies Vj shakes hand with Vi, so this graph is an undirected graph, meaning there is no direction. I don't need to differentiate between Vi comma Vj and Vj comma Dvi. They are both same, so they are undirected. And now in the problem, we had a condition that if A and B shakes hand and B and C shake hand, then A and C does not shake hand. What does it mean? So if you think of it, it's like if I have a vertex and a vertex, if I have a vertex A, vertex B and vertex C, if A and B shakes hand and B and C shake hand, then this vertex, then this edge A to C should not be there. So in other words, we call this kind of a thing a triangle. So the guarantee should be that the graph does not have a triangle. So there is no triangle in the graph. Okay, so this is the initial setup. And what is the question saying? Question is asking how many edges can there be. So the question is, how many handshakes can there be, which implies that how many edges can there be. So the problem boils down to a nice problem in graph theory. A graph on 2n vertices such that there doesn't exist a triangle. Prove how many edges can there be. Right? So if I remove the condition that there is no triangles, then how many edges can there be? It's like for any two of them we can have an edge. So it is of the form of n choose 2. Now, if I have to guess what is the maximum number that can be, I have to first try out some examples of graphs where the number of, there is no triangles, but they have a high number of edges. Now as we looked at last time, we saw that a bipartite graph where I partition the set of vertices into two parts, L and R, both of them having n vertices each, and between them I join any two of them, right? So we write V as L union R, size of L is equals to size of R equals to n, so they are disjoint, and the edge set is the whole, all possible pairs where one is coming from L and one is coming from R. So observation is that this one does not have a triangle and number of edges is n square. So hence we get a graph which is triangle free and it is a graph on 2n vertices and the number of edges is n square. So we kind of guessed that this possibly is the maximum number that we can have. And in fact, that is what we should be trying to prove. So we should be getting that n square is the maximum number and that can be attained also. But question is that how do you prove that statement? So this is where we were in the last class. Now to prove the statement, we will be using induction. So for that, first of all, we will be inducting on n. Note that the number of vertices in a graph is 2n. And what is the induction? We have to, as we have seen in the induction, we have to break up the problem into the cases. So let Pk be this thing saying that an undirected graph on 2k vertices has with no triangle has ordered. So this is a mistake here. This should be k square, has k square edges. Right? So this is the p case problem, and in that case we want to prove that for all k, prove that the statement pk is true. Right? So back to our induction basics. We have to prove it using the three steps, namely base case, induction hypothesis and inductive step. So again here is the pk and the steps to be done. Of course, the base case, we have to prove this base case for n equals to 1. We have an induction hypothesis. Now the induction hypothesis can be, of course, there can be different kind of induction hypothesis depending on what are the versions of induction that we are going to use. In this case, we will use the induction hypothesis where for some k, we have pi is true for all I less than or equal to k. So that means I have p1 is true, p2 is true, p3 is true, dot 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 till pk is true. Under the assumption that p1 to pk is true, can we prove pk plus 1 is true? So that is the induction version that we will be using. So using this induction, we will try to solve the induction inductive step. So start with the base case. Now can we prove the base case k equals to 1? If the base case k equals to 1, then in the graph there are two vertices and either they can have 1 edge or 0 edge. So the number of edge is less than or equal to 1, which is k square. Good. So that is what we wanted to prove. So P1 is true. So thus this can be, is not that easy to, not that hard to see that the base case k equals to 1 is true. Now the induction hypothesis, of course, that P1 to Pk is true. And using this, I want to prove that Pk plus 1 is true. So this is a very important note here. Whenever you have to prove induction, you should always start with an instance of Pk plus 1, what you want to prove. Not try to construct, start with an instance of Pk or something and construct a Pk plus 1. This is a statement, this is a very important note, and I will keep on repeating this thing for a few times. You don't face this issue when you are solving using induction for number theoretic problems. like we have seen till now. But whenever we apply the induction for combinatorial objects like graphs, this is a very important statement. So we have to prove pk plus 1. So we should start with an instance of pk plus 1. So in this case, we should say that, okay, let G be a graph on 2k plus 1 vertices without any triangle. And now we should use this graph and then use the induction hypothesis to prove that this graph has less than k plus 1 whole square vertices. Okay? So, for the inductive state, we have this induction hypothesis. We want to prove this inductive state. And we start with let G be a graph on 2 times k plus 1 vertices without any triangle. And we have to prove that in that case, G has at most k plus 1 whole square edges. Now we somehow have to convert this G to a smaller instance so that we can apply the induction hypothesis. So let's see how do we go about it. So first of all, if the graph has no edge, then the number of edges in this graph is 0, which is clearly less than k plus 1 whole square. So we can obviously assume that G has at least one edge. So let u comma v be an edge in the graph. So we have a graph on 2k plus 1 edges. We want to prove without any triangle. We want to prove that the graph has at most k plus 1 whole square edges. And we also assume that there is an edge in this graph. Now, there can be 3 kinds of edges in this graph. Number 1, the edge between u and v. There is only one such edge, of course, 1 or 0. And this, since we have assumed that there is an edge between u and v, that's an edge. There can be, if I have this graph, if this is the graph G, this is u, this is v, there can be 3 kinds of edges. Number 1 is this edge. Number 2 is a look at all the vertices other than u and v. So there can be edges from u to some edges, the vertices in the graph, and v to the rest of the vertices. So edges between u and v and the rest of the graph. And the third one is the edges that are within vertices which doesn't even touch uv. So the edges in the graph G minus v comma u. So by this notation I mean that I take the graph, I remove the vertices u and v and all the edges connecting to u and v. So I get the rest of the graph and that graph, right? So any graph can be split up into this ways. The edges between u and v, the edges between uv and the rest of the graph, and the edges in the graph G minus v comma u. Now I will count these edges in each of these 3 categories one by one. First of all, the first category is easy to see, that is just 1. What about the second category? So here we have assumed there is an edge between u and v. Now consider these neighbors of u and v in this graph. So if this is the graph here and I have taken out 2 vertices u and v from here, and I know there is an edge between u and v. Now I claim that there cannot be any vertex here which has neighbors with both u and v. If it had, then we would have got a triangle. But because we have assumed that G does not have any triangle, so no neighbor of u, no vertex in G can have neighbors with both u and v. In other words, u and v cannot have any common neighbors. So how does it look like therefore? So let me just redraw it again. So here is the graph, here is U, here is V. U and V there is an edge. Some of the vertices has edges with U, some of the vertices has edges with V, right? Some of them might not have any edge at all, that we don't know, may or may not have. But more importantly, every vertex here in G minus U can have an edge with at most U and V. The number of vertices here is how much? Yes, 2k. Because initially it was 2k minus 1, I have taken out 2, so this has 2k vertices. So every vertex in G minus V, U can have an edge either to U or to V. So in other words, the number of edges from UV to the rest of the graph can at the most be 2k. So in the classification that we did, the second category, that is the number of edges between UV to rest of the graph, can have at most 2k edges. This is where we have used the property that the G is triangle free very crucially. Now to complete the proof, the third step, okay, here again, we had G, which was a graph on 2k plus 1 vertices without any triangle. I picked out UV, which has an edge. Now look at G minus the vertex U comma V. Now that's the graph on 2k vertices. And since G did not have a triangle, this new G, rather this should be G minus UV, also does not have a triangle, right? Because the triangle cannot be produced by remove two vertices. So the new graph, which is G minus UV, is a graph on 2k vertices without a triangle. So by induction hypothesis, there can be at most k square graph edges in the graph G minus the vertices U comma V. This is where we crucially use the induction hypothesis. I start with G, remove two vertices to get a smaller graph. And in the smaller graph, I see that smaller graph has the same property. In the other sense that the smaller graph is the graph on smaller number of vertices and it has no triangle. So we can then apply induction hypothesis to claim that G minus V comma U does not have more than k square edges. So finally, the total number of edges in G is at most the edges in G minus the vertices VU plus edges between UV and the rest of the graph plus 1, which is the edge between U and V. And let's put them back. So this one is k square. Edges between G minus this one, this we just now proved is k square. The edges between UV and the rest of the graph is, in the earlier slide we proved it is 2k. So we have this is at most k square plus 2k plus 1, which is k plus 1 whole square. And hence we have proved what we wanted to prove, that the graph G. So wrapping up, what do we have? So we started with a graph on 2 times k plus 1 vertices without any triangle. We wanted to prove that the graph has at most k plus 1 square edges. Either the graph has 0 edges or at least 1 edge, and in either case we proved the number of vertices in graph is, the number of edges in graph is at most k plus 1 whole square. Hence proved. So we have used first of all graph theory to represent this problem so that we can visually work on it. Also, we have used induction on graphs to solve this problem then. And we proved that a graph on two n vertices without a triangle has at most n squared edges, which is same as the handshake problem, the answer of the handshake problem. In the next video, we will be looking at the other problem that we had talked about, which was the problem on tournament. Thank you.